Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to learn about ethers. We're going to learn about how to name them, how to make them, and then some basic characteristics that apply around them, like protecting groups and what's known as neighboring group effects. Okay, so that's what we're going to do in this video, and let's get started. So the first thing I want to talk about is the nomenclature of ethers. So the way that we name ethers is we look at an oxygen, right? And we consider the left and right side of it, right? So there should be an R on both sides. That's what makes up an ether. Remember, it's an oxygen that has an R group on either side of it, right? Remember it that way. So the idea is that there are certain types that are called simple ethers, and that is the case when they're either very easy to name because both sides of it are simple branching, or it's symmetrical. So for example, if I have, let's say, an ether like this, we would call this a diethyl ether. So that's a diethyl ether. Now, even if I had, let's say, a methyl and an ethyl side, well, it's still simple enough that we can name this. So what we would say is that we have an ethyl and a methyl side. So we have an ethyl methyl ether. So a simple ether is when you can easily name the sides and there's nothing tricky about it. It's not hard to figure out. There's no complex branching. That's when you go with this nomenclature. Now, some of them are actually simple, but they might look complicated. Let me give you an example of that. So let's say I have an alkene, ethene, specifically ethene, and then I have over here, like that, 3 carbons in a double bond. Well, if you look closely, this carbon is allylic, right? This is called the allyl carbon because it's next to a double bond. And when it's prop, when it's only 3 carbons, that's the simplest allyl that you could ever have. So I can call that right side an allyl. And when you have an alkene, 2 carbons, and it's double bond, that's known as a vinyl, right? This is the simplest vinyl you can have. Now, if you have more carbons on the left or right, then you can't use this nomenclature because these are the signature nomenclatures for the simplest form of these two names. Vinyl is 2 carbon alkene. If you have 3 or 4 or 5 carbon alkene, it still has a vinyl position, but it's not called vinyl anymore. Okay, you see the difference? So in this case, we could say we have an allyl vinyl ether. And everyone would understand exactly what that means. You have an allyl, which is a 3 carbon, double bond is away. Vinyl, which is a 2 carbon alkene ether. Okay, so here are examples of naming simple ethers. Now, when you get to more advanced ethers, like more complex, that's where it's not so simple to name it. So for example, to prove my point of a moment ago, if let's say I have this right here. And now this is easy enough to name. This is a butyl propyl ether, right? But what if I have, let's say, a double bond? Now this is no longer a vinyl. You see that? This is not called vinyl. It is a vinyl position. The double bond carbons are the vinyl carbons, but the name is not vinyl. It's more advanced than that, right? It's bigger than 2 carbons. So how we would name this is we call one side OR is equal to an alk-oxy group, alk-oxy. And so all we do is name it as a substituent on a parent. So this is called an alk-oxy group. Now, since I have 2 different sides, and one is a lot easier to name, right? The right side is a propoxy. I would say this is prop and an O for oxy, propoxy. So the way I would name this is I would say, okay, I have 1 for the oxygen. It's higher priority, right? You want to try to get it the lowest possible number. Here's 1, 2, 3, and 4. So let's say I had a BR here just to add more complexity. So we would have a 3 bromo, B before P, right? Propoxy. 1 propoxy, and then 1 butene. And now notice that this right here is an alkene and it has trans. The 2 groups off of it are opposite side. So we would say this is a trans 3 bromo 1 propoxy butene, right? You see that? So now we put this name together. we called the left side the parent. We did all the nomenclature rules that we normally would work from. Alkene has a higher priority, than the Br, but the oxygen has even higher priority than the alkene, and that's what we see here. Okay, so that's how we would name this, and it's called an alk-oxy group. And that's very common. Like, for example, if I have a benzene and it has an OCH3, we can call this a methoxy for the small OCH3 side, benzene. See that? Methoxy, benzene. So now I know I have an alkoxy on a benzene. And that's it. So these are examples of more complex nomenclature. So just remember, when you're looking at it, you have to find a side that's easier to name, and that becomes the alkoxy side. So it might be like tert-butoxy, for example, right? So imagine if I have, let's say, a ring system, and there's an O with a tert-butyl group on the oxygen. So we would say this is a tert-butoxy cyclohexane. See that? So the ring is the parent, and the alkoxy is a tert-butoxy. And that's it. So this is examples of how you name. So hopefully that's clear. Let's go on. Now, how do you make ethers? Well, the good news is, for the most part, it's all stuff that we've seen before throughout the semester. So that's kind of good for us. Now, the first one is if we use acid catalyzed hydration. But now there's a little twist here, because remember, we use this to make alcohol. But imagine if I have an alkene and I treat it with H+ instead of water in alcohol, ROH. It doesn't matter what the alcohol is, primary, secondary, tertiary. It could be vinyl. Well, then it's not an alcohol, right? But we could have an alkene there. It doesn't matter. So it's very versatile. All we're going to do is we're going to break the double bond with the acid, make a carbocation, and then have the alcohol come in. Right? So we do all that, and of course, as always, and by the way, step 2 is -H+, meaning when the oxygen comes in, it's positive, so we pull off the H with a base to make it neutral. And I've showed in the alcohol videos how we could do that. Very simple, by writing 2 -H+. Now, I want to point out that everything applies as always, all the basic rules. If you make a carbocation, you have to look out for rearrangement, ring expansion, ring reduction, methyl shift, hydride shift, and you've already seen some examples of that, and we'll see more after in this problem set. Okay, so that's A. B, another way to do it is oxymercuration. So we could take oxymercuration and actually achieve the same goal. Let's say we want to make an ether from this, then instead of, whoops, not H+, instead of mercury with water, we're going to have mercuric acetate, which is that right there, and we're going to treat it instead of water in alcohol. And once again, the alcohol is very versatile. It could be any degree, it could be different hybridizations, it doesn't matter. Okay, so this right here, we get the mercury coming in just like we did with the alcohol reaction, HgOAC2, actually HgOAC at this point. And now alcohol's coming in. That's the only difference, right? It's whether it's alcohol or is it water coming in. So this is primary, this is secondary. So we know that the second one in goes to the higher degree. Mercury leans away to the lower. And so we have HgOAC and we have OR. If I write step 2 -H+, I can make it OR. I don't have to show the H on it anymore. So this is all kind of review even from this chapter, right? So from here, then we just write NaBH4, and that will remove the mercury and put an H in its place, and we get an ether. So we can make ethers through acid catalyzed hydration. We have rearrangement. We can make ethers through oxymercuration. Remember the key here, why we use this? There's no rearrangement, right? And it's an anti-addition, right? Anti-addition. So the mercury and the OR are going to come opposite sides of each other. All right, so that was the ideas for this right here. Now, the next one, C, is not what you might think. So you might be expecting hydroboration, but there is no hydroboration. You can't make hydroboration from